Okay, welcome to the video solutions for example sheet 7, which is based mainly on the Doppler effect and sound waves. So if we look at question 1, basically this is telling us a helicopter has a siren that emits a sound with a frequency of 1 kilohertz. And what we have to do is calculate the apparent frequency of the emitted noise if it flies away from an observer at a speed of 100 miles an hour. So if we want to calculate what's happening here, then we need to use the equation for describing the Doppler effect. So this was given in the notes. It's basically the apparent frequency of the emission is equal to the fundamental frequency, or the frequency of the emission from the object, divided by 1 minus the voltage. The velocity of the between the two, the source and the observer, divided by the speed of the sound wave c. Okay, so this is the equation that we're going to use to calculate this apparent frequency. The problems we have at the moment is we already know this f0 value here. That's just the 1 kilohertz, so we can put that in the equation. We know the speed of sound as 340 meters per second. That's the standard one we use. It should really be given in the question. But if you assume here that c is 340 meters per second, then what we don't know at the moment is the velocity here. Well, we do know the velocity, but it's given in miles per hour. Whereas for this equation to hold true, this velocity has to be in the same unit as this speed of sound factor here. So basically, if we have c, if we use c is equal to 340 meters per second, then we have to express this velocity here as meters per second. So in order to calculate that, we need to know how many meters are in a mile. Well, there are 1600 meters equals 1 mile. Okay, so if the helicopter is traveling at 100 miles per hour, then it's going to be 100 times this value here. So basically, in meters per hour, the helicopter is going to travel 1600 meters times by 1 hour, which is going to be equal to times by 100, because it's 100 miles per hour, so it's going to be equal to 160,000 meters per hour. Okay, so meters per hour, that's a unit there. So to convert that to seconds, we just need to divide this number here by 3,600, because there are 3,600 seconds in 1 hour. 60 seconds in a minute, 60 minutes in an hour. If you multiply those together, you get 3,600. So our value for the speed in meters per second is going to be equal to 160,000 divided by 3,600, which gives me a value of 44.4 meters per second. Right, so now we have everything to populate our equation here. So if we want to write the equation out in full, it's going to be equal to f0, which is 1 kilohertz. So we have to convert that into hertz. That's 1000 hertz divided by 1 minus. Now, in this case, we have to be a little bit careful, because the helicopter is actually flying away from the observer. Now, this velocity here is positive if the observer and the object emitting the frequency are coming towards each other. So if they're flying away, we have to make sure that the value here is provided as a negative. So it's going to be minus 44.4 there, and then we divide that by our 340 meters per second. Okay, so if we calculate that, then we get a value of 884 hertz. Okay, so that's the solution to question 1. So let's now look at question 2. So here now we've got a runner running towards a street musician playing a guitar at a speed of 3 meters per second. So basically, right, so we've got a guy sitting down here playing a guitar looks something like that. So that's emitting the noise, and then the runner is badly drawn, is running towards him at a certain speed, but he's getting closer to the guy who's emitting the music from the guitar. Okay. So the musician is playing a note of frequency 800 Hertz, and what is going to be the perceived frequency by the runner? So once again, we need to go back to the equation we used in the previous question. So the apparent frequency is equal to the emitted frequency divided by 1 minus the relative velocity between the source and the detector divided by the speed of sound. So once again, if we look at what information we have here for this question, then basically we have this emitted frequency is 800 Hertz. We have the velocity difference between the two of them is given as 3 meters per second, and the speed of sound is given in the example sheet as 340 meters per second in the equations. So let's just fill these values into the equation. So we've got this is actually easier than the previous one because we're already given this velocity between the detector and the source in meters per second. So the frequency emitted is 800 Hertz. So I'm going to put 800 there, divided by 1 minus this relative velocity is 3, and we're dividing that by the speed of sound, which is 340 meters per second. So now in this case, because the runner is moving towards the emitter of the sound, this value here is positive. Okay, so if we calculate this, if we work out this equation here, then we get a new value of 807 Hertz. Okay, so the important thing to note here is that basically because the observer or detector is moving towards the source, then the frequency will always increase. So we've got an emitted frequency here of 800 Hertz, and that's going to a value of 807 Hertz. It's only a small amount because the speed of the runner relative to the emitter of the sound is actually much lower than the speed of sound. Okay, because the speed of sound is 340 meters per second, the speed of the runner is only 3, so the actual increase is actually pretty small. If we compare this to our answer for question 1 here, here we had the helicopter moving away from the observer, and so straight away that means that this frequency is actually going to decrease. Because the emitter is moving away, we're going from 1000 Hertz or 1 kilohertz down to 884 Hertz. Okay, and that's because of this differential. Also, because the helicopter is moving a fair bit faster, the size of the change, this is dropping by 116 Hertz as opposed to just a few Hertz in the previous one. So the size of the change is much greater because of this increase in the relative speed. So basically, this speed here is a much higher fraction of the speed of sound of the system. Okay, but that's how we do that. We just have to be very careful that we get the sign convention right for this relative velocity. And if you're moving towards somebody emitting a sound, that frequency will always increase. If you're moving away, it will always decrease. So these are things that you have to bear in mind when doing these questions. Okay. So now if we move on to question 3, we now have a speedboat which is travelling on a lake. So if I imagine looking at the top of the speedboat here, it looks something like this. So that's a windscreen on a speedboat and 2 people sitting in it. Looks like a smiley face now. So that's moving through a lake at 20 meters per second. So let's put that in there. And it's generating a bow wave with an angle of 5 degrees. Okay, so if I have a bow wave that looks like that, so the bow wave angle is always measured relative to a line kind of drawn through the boat here. So if I do that there, then it's this angle here is 5 degrees. It's actually bigger than an actual 5-degree angle, but it makes it easy to see on the drawing. So here what we're asked to do is we're asked to calculate the speed of the water waves on the lake generated by the boat. So the equation I need to look at here is the equation for the angle of shock waves. And so the equation that we learnt in class is given by sine theta is equal to c, which is the speed of the wave through the medium, so the speed of sound, divided by vs, which is the velocity of the source. Okay, so we have to be careful to understand which is which in the in the scenario we have here. Well, basically, in this case, the velocity of the source is this 20 meters per second here. Okay, and this angle here, theta, is the angle that this bow wave makes with the direction of travel, which is 5 degrees. So that leaves the value here, c, which is what we're being asked to calculate in the question, because it's the speed of the water waves on the lake. Okay, so if you create a wave on the lake, it's going to move with a constant velocity, and that is the speed of the wave. This is kind of uniform, it doesn't change, just as the speed of sound doesn't change or the speed of light doesn't change. So we can rearrange this equation now. So basically c is going to be equal to the speed of the source times by sine theta. Okay, so if we put our values into that equation, the velocity of the source is 20 meters per second. We don't have to convert that, it's already in meters per second, times by sine of 5 degrees. Okay, and if we calculate that, then that gives us a value for the speed of the water waves along the lake at 1.74 meters per second. Okay, and for a shock wave to happen, this speed here, the speed of the wave through the medium, always has to be lower than the speed that the object travels through it. So for instance, you don't get a shock wave generated by an aircraft that flies lower than the speed of sound. But you have to be travelling, the speed of the object has to be higher than the speed of the wave through the medium in order for a shock wave to be generated. So that's the important thing to consider for this question here. Okay, so now let's look at question 4. So now we have a jet fighter which is flying at Mach 2. So once again, we might want to just draw out a picture that shows what's happening. So here we've got a terrible picture of a jet fighter. Looks something like that. Okay, that's the jet at the back and the wing. So we're looking side on now at this one, and it's travelling this direction at Mach 2, which is double the speed of sound. And what we want to calculate here is the angle of the shock wave generated by the aircraft. So we use the same equation again. So we've got sine theta is equal to c divided by vs. So we're actually being asked to calculate this angle theta, so we can just put our numbers into the equation here. So there's two ways of doing this. One way is you could put in just the values of the speed of sound that we're given. So you could put in, so the speed of sound is 340 meters per second, and we could divide that by 2 times the speed of sound, which will be double this value, which is going to be 680 meters per second. And that would give us the correct answer. The issue I have here is actually the speed of sound at sea level in normal temperature and pressure is 340 meters per second. It will actually change as you go higher. Basically, as you fly higher, the speed of sound is actually going to decrease slightly because of the change in the air pressure. So we have to be a little bit careful here, but it doesn't matter because the equation still holds up. One way of doing it though is basically the speed of sound is going to be a value at any height above the ground. So if we know that the value here, or the value on the denominator of this equation, is always going to be double the value on the top, then we can actually just simplify this and sort of say sine theta is just going to be equal to a half. So basically it's 1c divided by 2c, because you've got c on the top. If you know that the denominator is twice the speed of sound, those c's cancels, so you just get sine theta is going to be equal to 0.5. Okay, so that then tells us that the answer, theta, is the inverse sine of that, and the inverse sine of 0.5 is going to be equal to 30 degrees. Okay, so basically if we drawing this here, we have sort of like a shock wave that is going to go out in all directions, but the angle of this to the mid plane of the thing is always going to be equal to 30 degrees. Okay, and that's how we calculate the shock wave for the jet fighter. Okay, so if we look at question 5, what is the apparent shift in frequency observed when a star emitting light with a peak wavelength of 530 nanometers moves away from the solar system at a velocity of 6,000 kilometers a second? What will be the apparent peak wavelength of the emission? Okay, so there's actually two ways to do this. Well, let's just draw it out first of all. So we have a star here that's moving away at a really high speed. It's 6,000 kilometers per second. That's going to be 6 million meters per second, because we need to multiply it by 1,000 to convert from kilometers to meters. So in the solar system is us with our telescope looking at the star, and basically what happens is this is moving so quickly that the frequency will change enough to change the colour of the emission. So it will actually go more into the red end of the spectrum, which is why this is called a redshift, and it's a known thing in astronomy for predicting the speed of stars, or the movement of stars away from us. So there's actually two ways we can calculate the first part of this question. The first one is when we talk about a shift in frequency, we're talking about the difference between the two frequencies. So here we have our apparent frequency, and here we have the emitted frequency from the object, basically. And the shift is just the difference between these two values. So you take this the initial value and you subtract the value that we have there, and that tells us what the shift is going to be. So one way we can do this is we can say, well, the apparent frequency here is going to be equal to f0 divided by 1 minus, it's minus v ds divided by c. And we can put all the values in here. So we've got f0 is, well, we need to calculate the equivalent frequency for this wavelength here. We can put in the speed here and the speed of light, and we could work it out that way. But we also have a simpler equation provided for us on the data sheet, which allows us to calculate the frequency shift. So here we have the frequency shift, which is what was asked in the question. Delta F is actually equal to F0 V ds divided by c. So it saves us having to calculate this and then subtract it from the original frequency again. We can just use this equation here to calculate what the frequency shift is directly, and we just need to substitute the values into this equation here. So first of all, let's deal with this f0 value, f0 value. So if we know that c is equal to f times by lambda, then this value here, f0, is going to be equal to c divided by lambda, where the lambda is this wavelength that we have up here. So it's going to be equal to 3 times by 10 to the 8 meters per second, divided by lambda, which is 530 times 10 to the minus 9. So we've got a very big number divided by a very, very small number. So that's going to give us an even bigger number. And that gives us a value of 5.66 times by 10 to the 14 hertz. Okay, so it's a really big value, as frequencies of electromagnetic waves in the visible spectrum always are. So now what we need to do is we can substitute that value into our equation here and add the other bits too. So now delta F is equal to 5.66 times by 10 to the 14 multiplied by our relative velocity between detector and source. So this is this value here, but remember it's moving away from us, so this is going to be negative as well. So it's multiplied by minus 6 million meters per second, and then we divide that by the speed of light, which is 3 times by 10 to the 8 meters per second. So that's going to give us a value for the frequency shift of 11.3 terahertz. Sorry, minus 11.3 terahertz, because we've got that negative value in there. Okay, so this is the change in frequency. So the new frequency is actually going to be what the original was here. So this f0 value was 5.66 times by 10 to the 14 hertz. But then we need to subtract 11.3 terahertz, which is 1.13 times by 10 to the 13 hertz. Okay, and that's going to give us what this actual apparent frequency is here. We're just going to be working backwards to work out what the apparent frequency here is for the observer, because it's going to be equal to the original frequency minus this frequency shift here. Okay, so the frequency is going to be lower because it's moving away, it's moving more into the red region of the spectrum, so we need to subtract this frequency shift here from this initial value here. And so if we do that, we're going to get a value of which will give us a value of 5.54 times by 10 to the 14 hertz. So now that's going to be our apparent frequency, and we want to work out what the apparent peak wavelength is of this. So we need to go back to our wave equation. So C is equal to f lambda. So lambda is equal to C divided by f, which is going to be equal to 3 times by 10 to the power of 8 divided by 5.54 times by 10 to the 14 hertz, which is going to give us a value of 5.41 times by 10 to the minus 7, which is equal to 541 times by 10 to the minus 9, which is 541 nanometers. Okay, so that's how we calculate that question. Okay, so now let's look at question 6. So here we've got a laser infrared speed gun emits a beam with a wavelength of 905 nanometers. Okay, so it's used to detect the speed of an oncoming vehicle. So we have, say, a car here which is moving towards some guy with a speed gun that looks like this. And the speed, he's going pretty quickly, is 102 miles per hour. So he's in trouble. And basically what we want to do is work out what is the frequency shift of the reflected signal. Okay, so in the previous question we used the equation for the frequency shift that delta f is equal to f naught VDS divided by C. So this is the frequency of the emitted wave, the velocity of the source, and the speed of the wave, so the speed of light in this case. But that was for a scenario where the emitted object was moving away from the observer. Here what we have is we have the observer, the guy here, is actually emitting the wave, reflecting it off an object and bouncing back again. So we actually use a slightly different variant of this equation, which just adds a 2 in front of it. So basically this is just the case for where we have a source that is being reflected off an object and then received again by that source. We have to have this value of 2 into the equation here. So once again we just need to make up, we can put the numbers into the equation. So first of all we need to calculate f0. So we have the wavelength of the light. So similar to the last question, we now have to calculate the frequency. So the frequency is going to be equal to the speed of light divided by the wavelength. So it's 3 times by 10 to the 8 meters per second divided by the wavelength, which is 905 nanometers. So 905 times by 10 to the minus 9. Okay, and that's going to give us a value of 3.31 times by 10 to the 14 hertz or 331 terahertz. Okay, so we calculated that. Now we need to calculate this velocity here between the detector and the source. So we have that in miles per hour. So once again, we know that there's 1600 meters in a mile, and there equals 1 mile, and there are 3600 seconds is 1 hour. So to calculate miles per hour in meters per second, it's the figure in miles per hour times by the number of meters in a mile and divided by the number of seconds in an hour. Okay, oh, so it's 102, isn't it, in this case, not 100, my mistake. So if we calculate that, we get a value of 45.3 meters per second. Right, okay, so now we can put those into our equation. So our frequency shift now, delta F, is equal to 2 times by 3.31 times by 10 to the 14 multiplied by 45.3 divided by the speed of light, which is 3 times by 10 to the 8 meters per second. And if we solve that, we will get a value of, that equals 1.00 times by 10 to the 8 hertz, which is equal to 0.1 gigahertz times 10 to the 9. Okay, so that's the solution to question 6. Okay, so now for question 7, we're looking at an ultrasonic beamforming scanner. So if you remember, we covered this in class. This consists of a line of transducers, and they're all triggered at slightly different times to give you a kind of wave or a pulse that is emitted from the scanner at a certain angle. And by slowly changing these delay times, you can actually create the kind of fan type scan that is representative of kind of classic ultrasound scans for babies and looking inside people and that kind of thing. So here we've got a line of transducers on our scanner. Looks something like this. So these are all regularly spaced, despite my drawing. And this space, we're told, is going to be 5 millimeters. Okay, so we want to calculate the time delay required between the emission of the sound pulses from the neighbouring transducers to obtain a scan angle of 20 degrees. And here we're assuming the speed of the ultrasonic wave through the medium is 1200 meters per second. Okay. So effectively we've got our emission angle here, so from the straight through is going to be equal to 30 degrees. Oh, sorry, 20 degrees, my mistake. And this is 5 millimeters. So, and the speed of the ultrasonic wave C is equal to 1200 meters per second. So if we go back to our notes, we can see that the equation that determines this was given as Tn, which is the delay time between an emitter and the nth emitter, is going to be equal to dn sine theta divided by the speed of the sound wave. Okay, so this is the time delay required. Now, instead of considering the nth emitter, it's probably easier just to think of the first one in the row and the one next to it. In which case, this becomes the time delay between the neighbouring scanners, which is what's asked for in the question. And so this d value here, the distance between the emitter and the neighbouring emitter, is just equal to 5 millimeters. Okay, so this is going to be 5 millimeters. Our angle here, theta, is given in the question as 20 degrees, and we've been given the speed of the sound wave through the material here, c, is equal to 1200 meters per second. So it's just a case of putting these values into the equation. So our time delay here, t, is equal to this value here, but this is in meters, remember, so we've got to convert our 5 millimeters to meters. So we divide that by 1,000, so that's going to be 0.005 meters times by sine of 20 degrees, and divide that by the speed of sound, which is 1200 meters per second. Okay, so if we calculate that, we'll get a value of 1.4 times by 10 to the minus 6 seconds. So it's a very, very short time between each one, but that's equal to 1.4 microseconds, because the microsecond is times 10 to the minus 6. So that's how we calculate that one. Okay, so they're the solutions for example sheet 7. So work through those, and if you have any problems, then get in touch by email. Okay, thank you.